Okay, welcome back. We are on Unit 5 on Vectors, Lesson 5. Today we're going to learn about dot product and its applications. Now, so far in Cartesian vectors, we learned how to add and subtract Cartesian vectors. We also learned how to multiply a Cartesian vector by a scalar. I hope you don't mind while I turn off the mood music. I forgot that was on. So today what we're going to do is we're going to learn how to multiply vectors together. There's actually a couple of ways in which we're going to do this. The first method that we're going to learn is going to give us a scalar, so the dot product. One of the most important applications of the dot product is mechanical work. Now, mechanical work, if you've taken physics before, then you've already encountered mechanical. Basically, mechanical work is the product of the magnitude of the displacement traveled by an object multiplied by the force applied in the direction of the motion. So in some cases, the force could be applied at an angle, and we would have to figure out the component in which it lies in the same direction as the displacement. So we'll go through and we'll see how this, when we learn the dot product, we can apply it to mechanical work and actually come up with answers to problems dealing with mechanical work. So some terminology, the dot product is for two vectors A and B. If we have a generic A and a generic B, then the dot product is defined, and we denote it as A dot. Yes, we do have to place the dot to denote that we are finding the dot product, is the magnitude of A times the magnitude of B cos theta. So basically, as mentioned before, we're multiplying the magnitude of A times the component of the magnitude of B that lies along A, okay, where the angle theta is in between 0 and 180. The dot product is a scalar. It's not a vector, so we can define the units accordingly. So again, I just want to reiterate, the dot product is a scalar, and you'd be surprised at how many times a lot of students in finding the dot product, they try and give me a direction, but remember, the dot product is a scalar. So let's take a look at our first example. Determine the dot product for each pair of vectors. So let's take a look at A first. First, looking at A, okay. So remember that the equation for the dot product of two vectors is equal to the magnitude of A times the magnitude of B times the cosine theta of the angle between them. Okay. So in our first example, A, so it's 30 is the magnitude, 20, and then cosine of 40 degrees. Okay, then is equal to, and we were to put this in our calculator, we would find that it's 559.6. Okay, remember it's a scalar, so we don't have to define any direction. Okay, so B, let's flip back to B, and I'll show you what we were asking. Okay, so we have this, so the angle between the two vectors M and N is 90 degrees. M is 60, N is 75. So the dot product for M and N is then equal to 60 times 75 times the cosine of 90 degrees. Okay, so if you were to punch that in the calculator, what you would find is it's equal to 0. Or if you even want to analyze this another way, we can say that the cosine of 90, okay, if you know this already, the cosine of 90 is 0. So multiplied by everything else, it's equal to 0. So this is a very important property, actually, that the dot product between two vectors that are perpendicular to each other is equal to 0. So just a few other properties that we can talk about, and that was the first one that I had mentioned, was the perpendicular property. There's other properties as well, such as the commutative property, which if you're taking the dot product of two vectors, they can be swapped. then if you have two or one vector that is the dot product of itself, it's simply the magnitude squared. Associative properties for scalars, and then distributive properties for the dot product. So in Cartesian vectors, if you have the dot product of two vectors, A and B, that are represented in its components, or its horizontal and vertical vector components, then we can simply multiply the horizontal plus the product of the vertical components in order to come up with the dot product. Okay, and these are vectors. I'm not sure why my arrows do not come out, but they should have arrows over top, so they are vectors A and B. So let's take a look at an example. Okay, so what we have here is we want to find the dot product of U and B for both A and B. Okay, so let's take a look at A. A, we want to find the dot product of U and V given its Cartesian vectors of U being 5 and -3, and U 4 and 7. Okay, so U dot V is then equal to 5 times 4 is 20 plus negative 21, which is equal to -1. Okay, so that's A, B. So simply, again, U dot B. If I was to even write this out, maybe this will help me too. U1, V1 plus U2, V2. Okay, so in this case here, we would have our second set of vectors, U, -2 and 9, and B is equal to -1 and 0. Okay, so we have -2 times -1 plus 9 times 0. 2 plus 0 is +2. Okay, so let's take a look at an application question for dot product. So Angela has entered the wheelchair division of a marathon race. While training, she races her wheelchair up a 300-meter hill with a constant force of 500 newtons applied at an angle of 30 degrees to the surface of the hill. Find the work done by Angela to the nearest 100 joules. Now, work is in units of joules, okay, and we have to make sure that we're always in our standard SI units. So in this case, distance is always in meters and force is always in newtons. Okay, so when we have that, then our work will have the proper units of joules, because joules is equal to a newton meter. Okay, so as mentioned before, work is the dot product, or the product of force and displacement in the same direction. Now, in a lot of cases, your force and your displacement, they're vectors. And so when we want to determine work, we would be, work being a scalar, we would actually be determining the dot product between the force vector and the position or displacement vector. So in this case, in this particular question, we're saying that the force, the magnitude of the force, okay, so let's rewrite this, the magnitude of the force times the magnitude, okay, of the displacement in the same direction, okay, as the force. So the force is actually applied at 30 degrees. So in this case, it's the angle of the force. So the force is cosine of 30 degrees. So they're 30 degrees apart, okay? So if we're filling this in, we now have 500 times 300 and cosine of 30 degrees, okay? And working that out in our calculator, and I've already got this worked out, is 129,904, okay, Newton meters, which is also joules, okay? So therefore, the work we always say the work done by Angela is, and we want to round it off, so it's already, we'll round it off, so we'll drop off this 4 at the end, so it's 129,900 joules. And there you go. One of the really useful applications of dot product is being able to determine the angle between two vectors if you're given the Cartesian form of the vector. Okay, so let's see how we can do this. So an example, this example here, A, what we have is G and H, and they're two vectors, and we want to determine the angle in between the vectors. Okay, so let's first write out the equation for the dot product using its magnitudes. So, okay, so there's our equation. Okay, cosine of theta using G and H instead of A and B. So now we're given that G is equal to 5 and 1, and H is equal to -3 and 8. Okay, so we want to find this right there. How do we go about doing that? Okay, so what we can do is we can rearrange this. So cosine theta, and all I've done is I'm going to move these two over here and leave the cosine, but I've just sort of flipped it. So it's G dot H over the magnitude of G and the magnitude of H. Okay, so just fix that up for you. That's an H. Okay, and this is another equation. I'm not going to make you memorize this. I think you can just memorize this and rearrange it rather than having yet another one. If you feel more comfortable having to memorize another equation, feel free, but I like just being able to rearrange it, and the less formulas I need to memorize, the better. Okay, so what can I do here? So I can find the dot product of G and H, okay, because I'm given the Cartesian, so I can go ahead and do that. And I can find the magnitudes of both G and H. So I can do it separately over here if you'd like. Okay, so this is the magnitude of 5 squared plus 1 squared, okay, which is the square root of 26. And here, I'll show you a square bracket, the square root of -3 squared plus 8 squared is equal to the square root of 73. Okay, and then if we find the G dot H, 5 times -3 plus 1 times 8 would give us, working that out, -7. And now putting it back into our equation over here, so -7 over the square root of 26, the square root of 73 as the cosine of theta. Okay, so we just want to find theta. So theta, and let's work that out, it's approximately 99.2 degrees. So the angle in between G and H is approximately 99.2. Now, since I don't have a check your learning at the end of this section, I'm going to let you do B on your own, and I'm going to tell you what the answer is. Okay, so take a little bit of time, pause it, try it out yourself exactly the way I did it, and then I'm going to go ahead and write the answer right here. So the answer is 90 degrees, and I hope you got that. So one other application of the dot product that we're going to learn today is it's called a vector projection. You could think of a vector projection as a shadow. Now consider the following diagram where the vertical arrows represent, say, a light from above a lamp, for instance. We can think of the projection as of this vector B. It projects onto the vector U as a shadow that V casts on U. Okay, so if the angle between U and V is less than 90, okay, then the projection U and V, or also we would use this notation, PRJ underscore U. So we would say this as being v on u is the vector component of v in the direction of u. So the projection is in the same direction as u. Now let's look at the case where theta is in between 90 and 180. So the direction of the projection of v onto u is actually in the opposite direction of u. The final case is if u and v are perpendicular to each other, then u casts no shadow onto u whatsoever, as you can see here. Let's take a look at an example of projections. Now in this example, I'm going to derive the equation for the projection of v onto u through this diagram right here. Okay, I just wanted to note that the C, for some reason, was not in the diagram, but now here it is now. Okay, so let's see how this is done. Okay, so let's redraw our diagram. So what we have here is the vector u, okay, and this is A, that's B, and D. Okay, so this is what we have. So what I have here is V. This is the projection of V onto U. So think of that as being the projection right there. I don't know if the diagram's that clear, but basically this part right here is the projection. Okay, so right there. Okay, so bear with me with my diagram. So AD is the projection of V onto U. Okay, so then we can say that, taking this diagram, we're going to label this theta, and this is 90 degrees. Okay, so theta and 90 degrees. So we can say that cosine of theta is equal to, so this is theta, adjacent over hypotenuse, so vector AD, okay, remember that AD is only a section of U, the vector U. It's the projection of V. Okay, so it's the magnitude of AD over the magnitude of V. Okay, so isolating for AD, I'm just going to bring this over here. Actually, I'll leave it as such. So we can say that V, the magnitude of V cosine of theta is equal to the magnitude of AD. Okay, so basically, that means that the magnitude of the projection of V onto U then is equal to the magnitude of V cosine of theta. So this is the scalar component of the projection, and what we need to do now is find the direction of U. Okay, so remember that it's in the same direction as U. Okay, so we can take U, and we know that there is some value, K times U, which is equal to 1. Okay, so I'm just going to separate the K. It's equal to 1. So I know the magnitude of K then is equal to 1 over the magnitude of U. Okay. So that means that the unit vector in the same direction as U, okay, is thus where K is, where we'll say K is equal to 1 over the magnitude of U, okay? So we can then conclude that the unit vector in the direction of U
is then, we'll say, is 1 over the magnitude of u times u. Okay, so basically we're dividing, in order to get the unit vector, we're actually dividing by the magnitude of u, of the vector. Okay, so projection of u onto v is equal to now v. Okay, so this is the scalar part of the projection, and this gives us our direction, which is the unit vector in the direction of u. There we go. And that will give us the projection as a vector, okay, and this part here is the scalar. If we were to go on to b, what we would find if the angle between u and v were between 90 and 180 is that we would get the exact same equation, only we would get the direction vector to be in the opposite direction of u, so it would be negative direction. So the moral of the story, and here they are, here's all of your equations for projection. This is the one that we derived, okay, and for angles between 0 and 90, you can see this is what we had come up with here. For just the scalar, and then for angles between 90 and 180, it's just the negative of the scalar for the previous equation. So over here, I just want to come back and take your attention back to this formula right here. Now what they've done over here is they've replaced these this part right here, so the magnitude of v cos theta. That is the same thing as saying v dot u, okay? And the magnitude of u is the same thing as saying u dot u, okay? So if you were given the Cartesian form and the components of the vectors, then you can simply just plug it into here, okay, instead of having to find its magnitude first. Okay, and so that concludes our lesson for today. It was a long one, but you did a wonderful job. So don't forget to do your homework, and we will see you next time.